What we discussed in the previous video is actually an example of the critical section problem. What's a critical section? Let's go back to the previous slide. See here, these three instructions that update, that increment the counter variable, or similarly, these three instructions that decrement the counter variable. These are what we call critical sections. We would not experience the problem if there was no context switch in the middle of this section. In other words, we should have a mechanism that tells the scheduler not to do a context switch once it starts this critical section. So, in other words, I wish I had a way of telling the scheduler something like, either do a context switch now or wait until I run this section, which is critical for me, at one shot. Please don't interrupt me. Please don't do a context switch in between. You want to do a context switch, do it now, or do it afterwards, but not in the middle. Okay? That's what we call with a critical section. So, in more general terms, not specific to that example on counter variable, in more general terms, let's consider a system where we have n processes. Okay? Let's enumerate these processes from P0 to Pn-1. Okay? These are not ordinary processes. These are processes that are related with each other. What do we mean by related? They are sharing some variables, like the variable counter in the previous case. Okay? So there is some dependency, in other words, between these processes, between these n processes. So each of these processes has some critical section on some shared data. Note that P0 and P1 could be sharing variable, let's say A, or data structure A. P1 and P2 could be sharing B. P2 and P3 could be sharing C, whatever. Or they may all be sharing, let's say, A. It doesn't matter, because even if the dependencies are on different variables or data structures, still, since P0 and P1 share A, I can say P0 and P1 are dependent on each other, because depending on the execution order, the outcome would be different. P1 and P2 has a similar relation, but through some other data structure, B. Still, I can say there is still a dependency between P0 and P2 over data structures A and B. So I cannot say P0 and P2 are unrelated because they don't have a direct relationship over some data structure, but indirectly still they are related. Anyways, so we are assuming that each of these processes has a critical section, and the processes may be changing for its critical section. They could be changing some common variables, updating tables, writing to files, to pipes, whatever, or doing inter-process communications. And when one process is in its critical section, no other process should be allowed to enter its critical section, because if it does, we may experience the problem we had here. So the critical section problem is aimed at designing a protocol to solve this problem we have discussed. So each process should have a mechanism. There should be a protocol between these processes to enter its critical section. And when it is done, it should be able to specify that it's getting out of its critical section. So there should be a mechanism for exiting the critical section. And after it has exited its critical section, for the remainder of the program, which is outside the critical sections, those parts of P0, P1, P2, whatever, could be run concurrently in the way the scheduler imposes. There's no problem with the remainder section. The problem is with the critical section. So we can say any process Pi, in this case, has a critical section, remainder section. Critical section, the program execution is composed of, we do something in critical section, then regular operation. If you need another critical section, again go into a critical section, again exit. So a process is switching between its critical section and normal sections, which is the remainder section. And this could happen any number of times. So this is true for any one of those processes Pi. To solve the critical section problem, we need to make sure that these three conditions we are going to discuss now hold simultaneously. The first one is mutual exclusion. So mutual exclusion says if one process is in its critical section, no other process should be in its critical section. So, in other words, a process is in its critical section in a mutually exclusive manner, guaranteeing that no one else is in the critical section. The second requirement is the progress requirement. If a process is in its critical section, and there are some processes that want to go into their own critical sections, the selection of those remaining of those other processes that want to go into their critical sections cannot be postponed indefinitely. That means the following. If, for example, P0 is in its critical section in a mutually exclusive manner, and let's say P1 and P2, they also want to go to their critical sections, they have to wait. Okay, we agree on that. They have to wait. But P0 cannot make P1 and P2 wait indefinitely. They may wait for some time. And pay attention, I'm saying sometime. I didn't put any time limit on that. I didn't say they should wait 10 milliseconds at most or 100 milliseconds. They will wait for some time. So we agree that there will be some delay for those processes. But it shouldn't be like P1 never ever gets the chance to go into the critical section. You cannot postpone a process's request to go into the critical section forever. And the third condition is somewhat similar. A bound must exist on the number of times that other processes can go into their critical sections after one process has made a request to go into its critical section and it's just waiting. That means the following. Okay, P0 is in its critical section. Both P1 and P2 are waiting also to go in their critical sections. Let's say the system selects P2 to continue next after P0. Okay, so in reverse, P1 is waiting also for P2 to complete its critical section. While P2 is running in its critical section, let's say P3 says, I also want to go into my critical section. Due to some reason, depending on the selection algorithm in the scheduler, maybe the scheduler might prefer P3 over P1 again. Maybe because of, let's say, some priority, some urgency, whatever. So P1 is still waiting. So P3 also goes in its critical section. Meanwhile, P4 arrives. P4 says, I want to go into my critical section. And let's say scheduler also chooses P4 over P1. So how many times can this happen? There should be a bound on this. You cannot say indefinitely that P1 should wait. It's not like exactly like condition 2 because there are some other processes that are going into their critical sections, but unfortunately P1, the poor guy, never goes into its critical section. That shouldn't be the case. Here we are assuming that each process executes at a non-zero speed. That means no process, let's say, gets stuck due to some other reason. Like, let's say, you want to do some input from the user has gone for lunch, in which people will definitely at some point return from lunch. But let's say the user has minimized that screen and never realizes that there is a process there waiting for input. That we assume such things are not happening. So every process, even slowly, is progressing at some non-zero speed. And also, never ever make assumptions on the speeds of the processes. Never say P1 runs faster or slower than P2. P1 completes in this much time. Don't make assumptions on that. We're not going to develop our algorithms based on such assumptions because typically such assumptions don't hold. So remember that these three conditions should be met simultaneously for the solution of the critical section problem. So, in the operating system, there could be different approaches for solving the critical section problem. You could have an operating system that allows preemption in kernel mode. That means one process wants to run a privileged instruction, so it switches to the kernel mode. For example, let's say, disk I/O. And while it's in the kernel mode, another process also wants to go into the kernel mode. So can you preempt that one from the CPU or not? It is possible to come up with preemptive systems that allow preemption there, or there are also non-preemptive operating systems that will not allow this. Okay, so the second process has to wait until the first one completes its kernel mode. Now, for the second case, when it is non-preemptive, if you have a single core in your system, then it's guaranteed that the kernel data structures are intact. So you will not have race conditions on these. However, we typically prefer preemptive systems because they're more interactive. They allow for real-time operations. However, implementing a preemptive kernel that will not get blocked, as we discussed earlier, due to critical section problems, that is difficult. Not impossible, but it requires the kernel to be more complex. So, one solution is provided by Peterson. Now, Peterson's solution actually does not guarantee that it will work, but it is good in pedagogical terms because it provides a good algorithmic description of the problem in hand. This solution works for only two processes. So remember earlier we said we had n processes. No, this solution works only if there are two such processes. We need to assume that the load and store instructions at the machine language level are atomic. That means when you say load, it is guaranteed that there will be no context switch before the load operation, the load instruction is completed. Similar is true for the store instruction. And these two processes share two variables. One is turn, and the other is actually an array of two Boolean values, flag. Turn will be indicating whose turn it is to enter the critical section, and flag will indicate if a process wants to go into its critical section or not. If a process wants to go into the critical section, it raises a flag which shows its intent to go into the critical section. But pay attention, it's not going into the critical section. It just says, I want to go into the critical section. And you cannot directly go into your critical section when you raise the flag. Still, you have to meet some conditions. We will discuss it now. So it just shows an intent to do it. And turn specifies whose turn it is. So turn will be typically initialized to 0. So in other words, of these two processes, P0 and P1, the initial turn will be given to P0. And the flag array will be initialized as false for both P0 and P1 because initially no one is in its critical section. Okay? So the algorithm is quite simple. When a process wants to enter its critical section, before entering the critical section, now in the critical section, remember, we have something like, for example, counter plus plus. Okay? So before doing that, you have to run this 3 lines here. So what does it say? This is true for both P0 and P1. So it's the same code for both P0 and P1. In P0, the value of I is, since we're talking about P0, I is 0. In, for example, flag I is 0. And the other one is J. So in other words, when P0 is running, it's making flag 0 true, and turn becomes, now if this is process Pi, J is the other one. So if this is the code for P0, you should read it like flag 0 becomes true, turn becomes 1. On the other hand, when you're reading it for process P1, it should be flag 1 true. In that case, turn should be 0. So always I is myself, J is the other one. Okay? So what's going on? Before going into the critical section, P0 sets its flag up, says I want to go into the critical section, which is correct. We're trying to enter the critical section. But before going into the critical section, it gives a turn politely to its opponent, to the other process. So it gives the turn to P1 and then checks if P1's flag is up and also it is P1's turn. If it's P1's turn and P1 wants to go into the critical section, definitely P0 should wait. Note that this is actually looks like an infinite loop here. Okay, so note the semicolon here. So P0 will get stuck here if P1 wants to go into the critical section. If not, it can. Now, what happens on the other side? Meanwhile, let's run P1 from our minds. When P0 sets the flag, sets turn to J, let's say P1 was running. P1 also, let's say, wants to go into the critical section. So it also raises its flag. Oops, sorry. If it has raised its flag, so flag J would be 1. And since the turn was given to 1, P1, turn is equal to 1 would be true. So true and true, P0 would be stuck here. Okay? But after P1 sets its flag to true, P1 also politely gives the turn back to P0. Because remember, from the point of P1, J is equal to 0. So P0 gives it, these are two very polite processes. It's like, I want to go to my critical process, please go ahead. And the other one says, I also want to go into my critical section, but please, you go ahead. Okay? Now, at that point, when P1 gives a turn, to process P0, flag would be true from the point of view of P0. Flag would be true. Flag 1 is true. But turn is now 0 anymore because P1 gave the turn to P0. Therefore, it's not equal to 1. So this second condition fails. And since this is an AND operation, this condition is false. Therefore, P0 goes into the critical section. Now P0 is in its critical section. Wait, let it remain in its critical section. Is it possible that P1 enters its critical section? Let's see. If P1, if we analyze this from the point of P1, remember P1 gave the turn to P0 here. So it's also in this while loop. So P1 is looking at the flag of P0, which is true, okay? And the turn belongs to whom? P0. It was P0's turn. So from the point of P1, this condition is true. Therefore, it will wait. Okay, so P1 waits. Till when? Until P0 completes its critical section and lowers its flag. Okay? When it lowers its flag, on the other side, from the point of view of P1, flag 0 is now false, independent of what the turn is. Now it can enter, P1 can enter its critical section. When it is done, it will also lower its flag. Okay. So the flag, pay attention, shows the intent to go into the critical section, but it doesn't specify whether you're in a critical section or not. It's not for that purpose. Flag shows your intent to go into the critical section, and turn manages whose turn it is, and two processes are kind enough to let the other one go ahead so that at some point they will also get the chance to work. So it is probable that the three critical section requirements are met. So mutual exclusion is preserved, as we have seen. Pi will enter critical section if and only if the other one does not want to go into the critical section, its flag is false, or the turn belongs to itself. And the progress requirement is satisfied. There is always some progress, and no one is waiting indefinitely by always giving the turn to other people, because there are only two actually.